Hi there, welcome to my channel Mandu to Fundu. In this video, I'm going to discuss about the solution for symmetric tree verification problem. Let's look at the problem description. We are given a root of a binary tree and we have to check whether it is a mirror of itself, like symmetric around its center. Let's take a look at this example 1. We have the root, and if we look at the left and right subtree, they are just a mirror of itself. So 2 2 and 4 4 and 3 3. So we are returning true in that case, but in this case it is not mirror of itself. If we look at 2 2 is matching, but this right child should have an equivalent left child on the right subtree, but instead it is also in the right side, so it is not a mirror, so we have to return false. So the number of nodes in the tree is ranging from 1 to 1000, and the value is minus 100 to 100. So at least there will be one node present in the tree. Let's take a look at the approach to solve this problem. So we have this input tree, and this is symmetric, so we have to return true. Let's see how we can return true. So the approach 1 is we can perform the in-order traversal on this tree. So we get this output. So if you look at it, this is the reverse order of the left subtree. Okay, so we can use a stack. When we process the left child of this root, we keep pushing that onto that stack. When we enter the right subtree of the root during the in-order traversal, we can pop from the stack and see whether the current element during the traversal is matching. So at the end, the stack will be empty, because as we see the corresponding element, we pop out. So finally the stack will be empty. So if the stack is empty, that means the tree is symmetric. That is one approach. In this case, the stack element should have the value, plus it also has a flag which indicates whether it is the left child of this node or right child of this node. For example, when we push the node 3, it should have the is left child to be true, because this is the left child of this node. But for node 4, this value is false. But this approach requires that at least half the size of the tree's stack space, in addition to the system's stack space, because we are making a recursive call. Each call will create a stack frame. So this is approach 1. And in the case of approach 2, we can traverse both left and right subtree simultaneously. For example, when we begin, we start the traversal with these two nodes. Then recursively we go down and compare. So whenever we each recursive call, we compare the current nodes. If they match, we proceed further down. Otherwise, we return back immediately saying this tree is not symmetric. So this one, it requires a stack space because we are making a recursive function call. So the space complexity is order of log n. Let's look at the flowchart. Input for this procedure is root of the left subtree and the root of the right subtree. So we call it as L node, R node. And first we initialize the return value to true. Then we check whether the L node and R node both are null. In that case, we return true, because the empty tree also symmetric. and then if not, then we check whether either one of them is null. In that case, they are not structurally same, so we return false, saying that it is not symmetric. Otherwise, we compare the node value of L node and R node. If they are not equal, then we return false. Otherwise, we make a recursive call with the L nodes left and the R nodes right, so that they form a mirror reflection. So that combinations we are using to verify whether it is a mirror symmetric or not. So we assign the return value to left, and then we make another recursive call. In that case, we pass right child of the L node and the left child of R node. Then we assign the return value to the right variable. Here we check whether both left and right are true. If so, we return true. Otherwise, we return false. Let's move on to coding. First, I call the symmetric helper function with roots left and right child. And next, I'm defining that asymmetric helper function. It's the left node. The node which is in the left subtree is called left L node, and the node which is in the right subtree is called R node. First, I check whether both are nil. If so, return true. Next, I check whether either one of them is true. In that case, both left and right subtrees are not structurally same, so we return false. Next, I check whether the L node value and R node values are same, and then I'm making the recursive call to check whether the next level. Next, I make a recursive call to check whether the next level is symmetric. So in this case, I'm passing the L nodes left and R nodes right in one call, and in another call I pass the L nodes right and R nodes left. If all of them are true, then I return true back to the symmetric function, otherwise it will return false. Okay, I missed the return statement. Next, I am going to run the test cases. Okay, some compilation error. Okay, let me rerun again. Okay, all the tests passed. Next, I'm going to submit this program. Cool, this program is accepted. Next, I'm going to do the code walkthrough with sample input. Let's do the code walkthrough for this input. So we have 1, 2, 2, 4, 3, 3, 4. So the tree looks like this. So if you look at it, the left subtree is the mirror reflection of the right subtree. So the symmetric function is called with the root node, which in turn, which creates this frame 0, and which in turn calls the symmetric helper function, which triggers the creation of this frame. So the symmetric helper function is called with the left and right child of the root node. Okay, so when we enter that helper function, we check whether these two are nil. They are not. Either one of them is nil. That is also false. So we finally come to this part where we check whether both the values are same. Yes, they are same. Next we make another recursive call to verify whether the childrens are symmetric. So for this left subtree, this left child, and for this right subtree, this right child are mirror reflection. So we pass these two nodes and check whether they are same. So both are same. So that triggers the creation of frame 2. So next we check whether the childrens are symmetric. So for that we have to check whether this node and this node are same. So with respect to this node, this is the left child, and with respect to this node, this is the right child. So we pass these two nodes to the symmetric helper function and these two nodes to another symmetric helper function call to verify these four are symmetric. Okay, that's what we are doing here. So the first call, we pass the left subtree's left child and the right subtree's right child. Both are same, so they will be returning true to this frame 1. And another recursive call, the right child of the left subtree's root and the left child of the right subtree's root, these two nodes will be passed and both are same, so they will be returning again to true. So basically this one returns true and this one returns true, and this is also equal. So finally the true will be returned back to the asymmetric function and we get the expected output true. Next I'm going to do the time and space complexity analysis for this solution. So in order to determine whether the tree is symmetric or not, we have to traverse all the nodes. So the time complexity is order of n. And next we do the space complexity analysis. So it is order of log n. The reason is, if the tree is complete binary tree, we have to create log n number of stack frame. We have to make that many number of recursive calls. So we use that stack space. So, but in the case of skewed tree, it will be just order of 1, because first recursive, when we make a first recursive call, at that time itself we return immediately because the next level itself is not symmetric. So it will be always order of 1 for the skewed tree. So for the worst case scenario, it is order of log n. Thanks for watching this video. Have a great day.